Emitter current and the collector current and base current can be represented with the gain beta values like this. And if we add the time transient characteristic to this, which is diffusion capacitance and the junction space charge capacitance, then we can add those two terms on this charge control model to have this, right? So in this figure, we can see that in the DC model, we have to add the charge control and the space charge capacitances on these terminals. And we end up with the equations, something like this, right? Now, we have discussed about the saturation, less than a little bit, and then today we are going to give you the examples of these saturations. And in this, let me just read this. We just define the base current, saturated base current, as IB total minus IC over beta F. If you divide the collector current with the gain, then it's going to be the base current, right? So this is the normal base current, and this is the base current total. So if you subtract out the edge of saturation component to the IB and define QS, small qs, as total and reverse total minus IC tau F. Okay, this IC tau F is corresponding to the charge, forward bias charges on edge of saturation. Okay, so first order approximations, we can get, this is important equations we can see. The saturation current, base current, is going to be related to two terms. Okay, one is the characteristic time and time dependent time like this, and then tau here, the tau is can be represented with this, with the equation. For the details of this derivation can be found in the literature. Okay, so this is a saturation characteristic time, and let's just define the beta and beta values for the forward bias and the reverse bias or something like this, and then we can relate this saturation characteristic time with to the beta values. Okay, and if you put the typical numbers on this, we have 3 nanoseconds as the saturation characteristic time. From the device point of view, behind the saturation, the stored excessive saturation charge has to be represented with this equation. Okay, and to bring saturate a device out of saturation, which means if you take the reverse voltages or current to switch, for the switch, then this charge, the stored charge beyond the saturation, this charge must be removed. During this saturation delay, we call that the saturation delay, because with this switching, until the saturated excessive saturation charge is removed, the the device is not going to respond to the input. Okay, so we call this the saturation delay. And then the device has to work negative base drive should work to remove the charges. And this is the current as we shown here, the current, okay. So this is the current, and then the initial current can be represented with this, and then the switching current is going to be represented and then this has to go to 0. Okay, so let's see. Let's talk about this a little bit later, and then let's go to the examples first. Now, forward by active mode example, circuit is going to look like this, and then at time t1, 5 microamps has been applied to the base, and then at the t1 it is increased to the 10 microamps, and let's see what's going to happen. And this is a device characteristic, it is given. Okay, the beta f is 50. For example, forward characteristic time is 0.1 nanosecond, and base forward characteristic time is 5 nanosecond, which is come from the multiplication of this 2. Okay, and approximate diffusion equation is, we are going to use this current equation. All right, as given in the earlier discussion. And so for the QF, this is a misprint. It should be big F. The current is going to go like this, and so this is a 25 picocoulombs, and then it's going to increase to 50 picocoulombs, and the QF is going to be represented with this equation. This is the first order differential equation. It's easy to solve. This equation is easy, and then we can deduce the A, and then the final equation is going to look like this. So the current, the collector current, has to be represented with this equation, okay, with a time, and then tau BF is given in the calculation. So this is the final answer that we are going to have. Now, in the saturation model, we have, this is the device characteristic, and then we increase the base current from 10, 50, 100, 200, 500, and then we measure the collector current. It's 0.5 or 2.5 is the milliamps, and 5. But beyond this, it is saturated, so that the collector current is no more than 10 milliamps. Okay, so at this saturation case, we set the equation like the charge of saturated, the charge is going to be reverse or forward minus edge of saturation. Okay, this is not going to contribute anything to the current, so we subtract that. And then this is the equation that we have. And the steady state, this is the steady state equation. And this is the situation that we have. In the base, the bias slope has been shown here. Okay, the charge state. So this is the extra saturation charge, the shaded area. Okay, so in the final example, with that, we can deduce the saturation characteristic time like this, which is a 3 nanosecond as before. And then this is the equation that we try to solve. And we put the numbers, and then we have IBS1, and then QS1 is 900 picocoulombs, and then IBS2, we switch the device, and that switching has been given in this example. Okay, the first example here, like this. This is exactly the same one. And we can define the charges QS2, and the total QS is going to be total charge consists of two terms, the QS2 and the QS1, and then this is the equation, and we can from this equation we can have the time delay, which is 2.37 nanosecond. So this is the charge with respect to the time, and it has been 900 picocoulombs before we start switching at the T0, and then we switching the device like this. Then this has to be going down, and to eliminate all the excess stored charge, it takes about 2.37 nanosecond. Then at this point at T1, the stored charge is going to be 0. So this is how we can solve the saturation switching characteristic. And then the tracer curve that we just left. This is the collector current, and this is collector emitter voltage that we apply. And then if you fix the base current, and with the application of the voltages, then at the 1, obviously, the collector current is saturated. After 1 is saturated. And then before that, the 2 and 3 is shown like this. And then if you, this is the base region, and then it represents the charges, okay, in the base region. And after the saturation, it has the curve is fixed like this. 1. The slope is fixed, and then if you increase the voltage, it just increase the level with the same slope. And before saturation, it has a different slope. Okay, 2 is showing like this, and then if you draw the 3 cases, then it should show the slower slope than the that of number 2, of course. And then the important thing is it is fixed to the number 1 after saturation. The slope is going to be fixed, so that the charge, which is the derivative of the slope of the charge, is going to be saturated. It should have a constant values. Now we have a little bit different situation here. We just fix the voltage. Here we just fix the current at the base. Now what happens if we fix the voltage between emitter and base, the input voltage? Then voltage fix means this pinpoint has been fixed. Okay? So it is not going to be altered by changing the collector emitter voltage. But after it is saturated, the charge has to show something like this, number 1, which is the same to this, after the saturation. But before the saturation, now the slope is going to get slower, and then the way to show the slope slow is to have different values at this space charge region, and this space charge region, the point has to be fixed because we fixed the base emitter voltage. So now the curve is going to be, the line is going to go up and up as you decrease the collector emitter voltage, of course, naturally. Okay, so that we have a slower slope. That's what happened physically. Okay, and then the examples shown here is the actual calculation, how we can derive the delay time. With this examples, you can have an idea how we can calculate the delayed time. Okay, and then most of the bipolar transistor is used for the switching. It has a faster, the bipolar transistor shows a faster logics than the MOS transistor because it works at the high voltages. So that the switching characteristic, in other words, the delay time is very important in the actual device. Okay? And the next chapter is has been devoted for the bipolar transistor 2, and the current gain is the first topic, and we have discussed about this current topic last time, so we we are not going to discuss it again. And after the current gain, the second topic was high-level effects. And then it has 3 terms on this, the sub-subject. The early effect, which is a high-level injection at the emitter injection, emitter voltage, high voltage of the emitter. That is going to be called the early effect. And then it's basically related to the extra electrons, which has been injected to the base across the space charge region between the emitter and base. And that extra density, charge density, the charges is going to roll off, ruin the gain of the bipolar transistor. That is the early effect. Okay, you can read this. And the high level injection at the collector, that is the Kirk effect, is once again is related to the extra charges which can happen on the on the base, okay, by the injection. Now, the next topic is the base current, and the base current it's just a ohmic drop. It works as an ohmic drop, so that the actual voltages between the base and emitter has to be diminished by the amount of this IR drop. So this dotted line is going to be the expected as beta values. That is the relationship between the collector current and the base emitter voltage, input voltage. But at high voltages, it just roll off a little bit from the ideal curve just because of the ohmic drop. Ohmic drop is always there, but it becomes significant as the voltage increased or current increased. So that's why it shows the just off the ideal curve and at the high voltages. So at high, if you want to fabricate a device working at high voltages, you should be careful about the resistance happens in the base. Now, we are in a dilemma. If you want to reduce the base resistance, then you have to increase the dopant concentration in the base. But as you see in the Gummel number, which is exactly the total amount of the dopant in the base, you have to have a low base concentration of the dopants to increase the beta values. So this has to be optimized in some sense if your device is working at high voltages. At low voltages, you have to worry about the space charge recombination. So that has to be optimized to make this low voltage operation beta values small. The off deviation from the ideal curve small. Okay. Now the next topic is ever-small model, and this is nothing but a derivation of the terminal current. Like this is the final equation that you can get from this ever-small model. Ever-small model, and then this alpha is something like the gain beta that you have been used formerly. Okay, and this is a total equation, but for example, this is alpha and the reverse alpha. Okay, and example, suppose we forward bias the emitter base junction, reverse bias the CV junction, that is the normal mode, and then IR, we just neglect the IR values, then the model reduced to this simple equation. Okay, then we can get the terminal current to the base, something like this. That is the use of ever-small model. So the ever-small model may be used under all junction bias conditions to estimate the terminal currents. Okay, that is very similar to the charge control model that we have derived in the former lectures. The next topic is frequency limitations, and then it has three frequency limitations. One is the base transit time, and emitter capacitance charging time. Okay, and then collector capacitance charging time, and then it's all related to the RC delay. So you can read on this, and then the collector depletion layer, transit time. It's basically related to the three regions: emitter, base, and collector regions. Time dependent, the time dependent delay, RC delay. Okay, so you just read this. Hybrid PI equivalent circuit. Well, this is just an equivalent circuit. Now, the final topic in this chapter is going to be the scaling bipolar transistors. Scaling. We have talked about the scaling in the MOS transistor, and then we have seen that in MOS transistor the gate length is directly related to the scaling. Okay, in order to have small gate length, we also have to change in the vertical section, like junction depth and the gate oxide thickness, and the dopant concentration, things like that, which is related to the vertical scale. If you want to change the scale in the lateral dimensions, you also have to change the scale in the vertical directions in order to keep the electric field constant. And that electric field is related to the device characteristic, physical reactions of the device. So in MOS transistor, it is obvious. We have to change in the lateral dimension the first. And accordingly, we have to change the vertical sections as well. Now, the bipolar transistor scaling is a little bit different from what we have seen in the MOS device, in the sense that the intrinsic device is the vertical. Basically, bipolar device is the vertical. The MOS transistor is basically the lateral. Okay, scaling of lateral dimensions, as we considered in MOS transistors, does not improve the intrinsic device. So, therefore, scaling of the intrinsic device implies we have to change the base. This is the base width, okay? The emitter edge and then base collector edge. This is the width of the base. And that width is as important as the gate length in the MOS transistors. That determines the device gains and everything. We have seen that if you make this thing long, then the injected electrons, which has to cross the base space charge region and the base neutral regions to reach the collector, it is not good if you have a big base width, right? So the scaling naturally related to the reduction of the base width, but the base width is already 1,000 to 3,000 angstrom in modern devices. It means that this width is basically controlled by the diffusion process or implantation process, which is not the same to the case, MOS case. In MOS case, the gate length is determined, controlled, or modulated by the lithography and etching technique and the thin film deposition technique, things like that. But in bipolar transistors, the width, which is most important in the bipolar transistors, this width is controlled only by the diffusion process. And that is not that difficult, which means it is easy to get 1,000 and 3,000 angstrom. But in MOS transistors, we have to develop many techniques, such as deposition thickness control or lithography patterning technologies or things like that, to have this sub-micron dimensions. So that's why the bipolar transistor has been developed first before the MOS transistors, even though the MOS transistor idea has been developed prior to the bipolar transistors. I mean, in the industry, it has to appear in the industry first, before the MOS transistors. Anyway, so already we have sub-micron base width. So fundamental limits occurred around the 300 angstrom. 300 angstrom is about, say, 20 or 30 30 atoms in height. So this is a fundamental limit we can think as a thickness control, right? So scaling to these dimensions will require extremely tight process control. We have to be satisfied with the 1,000 and 3,000 angstrom in bipolar transistors, maybe, because we have to sacrifice too many things to control, to have this extremely tight process control. Okay, lateral scaling is employed in bipolar transistors, however. This reduces the device size, okay, reduce the parasitic capacitance. We keep on doing it, but we obviously have some limits in the bipolar transistors. And most importantly, the bipolar transistor is not used for the integration of the device because bipolar itself is larger than the MOS transistors. It's not beneficial to get a high-level integration with the bipolar transistors. And the MOS transistors, the electrical functions or characteristic of MOS transistors have been improved to some part become equivalent to that of a bipolar. So there is no means, there is no there is no need to make a high-level integration with the bipolar transistors anymore. Okay, so the scaling of a bipolar transistor is not considered to be important these days. Well, the summary. Bipolar transistors are low input impedance, current controlled device. Okay? And MOS transistors is basically the capacitor, MOS, vertical capacitor. But a bipolar transistors, it works in the electrons and holes at the same time, is a current device. Transconductance is always higher in the bipolar than the MOSFET. So it has been used for the logics. But in the modern device, the transconductance of MOS transistor, it becomes equivalent to that of a bipolar transistors these days. So it not becomes important. Bipolar devices are typically used in the fast logic, that is a discrete logic circuit. Of course, we have a lot of beta values. Because they are larger physically and consumes more power, bipolar ICs are generally restricted to less complex functions than MOS ICs, especially for the integration of the transistors. Nobody is using for the bipolar. Well, maybe input and output subsidiary logic circuits, maybe we use the bipolar transistors for the protection of the MOS transistors. Okay, they'll wrap up the bipolar transistors. We rather run fast on this bipolar transistors. And on the final lecture on the 31st, I'm going to provide you the past exam, and then I'm going to talk about the TFTs, thin film transistors, which is not not that is not a bipolar transistor. It's rather, we can say this is MOS transistors, but it's fundamentally different from the MOS transistors in terms of the working principle. And this thin film transistor is very important for the display devices. Okay? So we are going to talk, we have talked about the MOS transistors, we have talked about the bipolar transistors, and at the final lecture, I'm going to give you the discussion on the thin film transistors, which is basically MOS transistors, but fundamentally different. And in the modern technologies are very important. Okay? And then we are going to have a dead week in the next week, and then we're going to have a final exam on the 12th of June. It's about the 1 hour exam. You can bring, it's open note, open book, open internet. You can use anything you like. Okay, I'll see you on Wednesday then.